I get it. All right. So, in your notes packet again today, I shouldn't say notes packet, excuse me, in your notes, your notebook, binder, wherever you're taking the notes today. And so we'll start with kind of a same problem as yesterday. So, Polito's Pizza. Yesterday we found the perimeter of one slice. Today I want you to find the area of one slice of pizza. Okay? So yesterday was perimeter, today area. Go. All right. So,
It's right there.
It's right where? Oh, I see it over there. Yeah. Okay. So, area of the circle is going to be pi r squared. So that's going to be 14 squared is what, 196? 196 pi? Yes? Okay. How many pieces of pizza in a full Polito's pizza? 8. So we're taking, we want 1/8 of that. Okay. Does 8 go in there? 224, not nice and pretty. So we can only divide by 4. So then that would be approximately, what would that be? So 4 would be 4, carries 9, 49. 49 pi over 7, or 49 pi over 2. Which is approximately, need a calculator. Agree? Yes? No? You have no clue, you didn't even do it. Don't lie to me.
I didn't know.
Lie to me. A little sunshine my way. Okay? Yeah. So, today, we're going to talk wheels and belts and pulleys and all that fun stuff. So, in order to get us ready to go with wheels and belts and pulleys and all that fun stuff, here is Mrs. Hill cruising on her new scooter at a maximum speed of 15.5 miles per hour around the crazy streets of Wausau. At this speed, how many revolutions per minute are her wheels rotating? Revolutions per minute. So that means we got to go by. We got inches, so we got to change miles. Now I'm in feet. Now I'm in inches. Radian. All right, let's see. Miles goes away. feet go away. Should use purple. Miles, feet, inches, radians, hour. Revolutions per minute, that's what I want. All right, let's calculate. Times 80 times 12 divided by 4.25 times 25 times 60. I got 612.952 RPMs. Yes? Anybody back me up on that? Yeah? 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 So that's one wheel that's rotating like that. Okay? Those wheels are both the same size on that scooter. Okay? But not always will we have the same size wheels rotating. Okay? So today we're going to talk about the belt on an electric motor is connecting metal wheels with radiuses or radii of 2 inches and 5 inches. So it looks like the picture up there in the upper right hand corner. Okay? The rotational speed of the larger wheel is 120 revolutions per minute. Okay? So that's its angular speed. Okay? So we want, that's the rotational speed, excuse me. We want the angular speed of the larger wheel in radians per second. Okay? Well, it's rotating at 120 revolutions per minute. One revolution is 2 pi radians, and 1 minute is 60 seconds. Revolutions goes away, minutes goes away, leaves me with radians per second. That's where I want to be. That reduces down to be 120 divided by 60 is 2 times 2 pi is 4 pi radians per second. So the big wheel is going around twice every second. Okay? Which makes sense because it's going 120 RPMs, which is twice every second. Okay? If you decided to give me decimal approximation, it would be that. Which one do you think we like better? 4 5. Cleaner. Okay? Cleaner. Nicer. Nothing wrong. Okay? What is the linear speed of the belt? Well, the belt is going at the same speed on both pulleys, right? Because the belt can't be going faster here than it is down here, because it's all connected. Okay? So it's going the same speed. So let's find that linear speed in inches per second. Okay? Well, the big pulley is rotating at 4 pi radians per second. And the big wheel had a radius of 5 inches. So that would be my radius then for that one. And now I'm in inches per second. So that is, the belt is traveling at 20 pi inches per second. Yes? Okay. Which, if again, if you wanted to decimal approximate that, that would be 62.832 inches per second. Agree with me on that? Now, based off of that, because that would be the linear speed of the smaller wheel, so based off of that, we can now find the angular speed of the smaller wheel. So the belt is traveling at 20 pi inches per second. Scrolling back up, the radius of the smaller wheel was 2 inches. So the smaller wheel is spinning at 10 pi radians per second. So the big wheel was spinning at 4 pi. The smaller wheel, because they're connected, the smaller wheel has to spin faster to keep up with the belt that's spinning it. So the smaller wheel is spinning at 10 pi radians per second, which would be approximately 31.416 radians per second. So it is spinning much faster than the larger wheel, which makes sense because they're connected. They're not independently spinning, okay? They are spinning together. And so the bigger one is spinning at a rate, the smaller one has to spin faster to match up with that same linear speed. Okay? The way I think about this is, no matter which one we give you, you've got to work your way to, come on, why are we jumping today? Act like we've used each other before, Mr. Smartboard. Okay? So if you start on the big wheel, which we did, we started as a point on the big wheel. To get to the smaller wheel, we have to follow what's connected. So we first got to the belt, because that's what's connecting them. Then we got to the smaller wheel. Okay? So you first have to find the linear speed of the belt or the chain or whatever's connecting the two wheels, then transfer that over to the smaller and find whatever. Okay? With that being said, here we go. 4-inch diameter pulley on an electric motor that runs at 1,450 revolutions per minute is connected by a belt to a 9-inch diameter pulley on a saw. Find the angular speed in radians per minute of each one. Find the speed of the saw, so saw arbor, that is That's where the saw is. And then find the speed of the saw in revolutions per minute. Okay? Go for it. I'm guessing you got that one. Right? Okay. That's my 4-inch pulley. Okay. Now we got to figure out the angular speed of the 9-inch pulley. Okay. The only thing that we know is we know that the 4-inch pulley is spinning at 2,900 pi radians per minute, which means the belt is doing 2,900 pi radians per minute, which means the belt is traveling at, it was a 4-inch diameter, so that is wrong side. Which means my belt is traveling at 5,800 pi inches per minute. Okay? Then, this is where, side note, it will help you to kind of do your crossouts. So I'm on the belt now. That's my linear speed. Because I'm on the belt, I can go to the other pulley. The other pulley was a 9-inch pulley. And now I'm in radians per minute of the 9-inch pulley. So 2 times 2,900 divided by 4.5 would get me 4,049.164. So 6, 1, 9. Questions on either one of those? Does it make sense that the smaller one is spinning faster? If they're spinning at the same speed, same linear speed, the smaller one has to spin faster to go as far. Okay? Find the speed of the saw in revolutions per minute. Okay, so now we're going to take this 11,600 pi over 9, and we're going to multiply that. Oops, excuse me, we should put a label on there. And we're going to multiply that. That was radians per minute. We're going to multiply that by 2 pi radians is 1 revolution. So I get 5,800 over 9 revolutions per minute. Which is approximately 644.4 repeated revolutions per minute. Okay. Questions, comments, concerns, clarifications? Chain drive on a bicycle. Okay. How far in feet will the bicycle move if the pedals are rotated through 2 full rotations? Assume the radius of the bicycle wheel is 13.2 inches. Let's talk this one through. Okay. So the pedals are going 2 rotations, right? Okay. So that is where we're starting. I don't know why it's jumping every time I move it. So we are right now right there. That black X is going around 2 full times. Where do we need to end up? Where do we need to end up? What are we looking for? We're looking for what? Nope. Nope. What are we looking for? Read the question again. We're just looking for feet. But where are we looking for feet? Have we all ridden a bike before? Yes? Or seen somebody ride a bike before? Do we know the concept of a bike? Okay? Spin the pedals. What happens? Bike moves forward, right? Okay? So we need to know how many feet we traveled by spinning the pedals twice. So where do we need to end up? That we starting with the black X, where do we need to end up? Because that's going to tell us our path that we have to get there. We got to see it. We got to end up on the wheel. Where's the wheel in our picture? Wheel's attached to that one, right? Right? Okay. So we need to end up there. How do we get there? Go through the chain. Okay, so let's go through the chain first. Okay, we know that the chain has moved 2 revolutions, right? We know that 1 revolution is what? We know that on the pedal, 1 radian is how much? 4.85 inches. So what do we have now? Inches of what? Where are we now in our diagram? We're at a distance. What distance? On the chain, right? Okay, so we're on the chain now. So that tells us how many inches the chain has moved. Okay? Chain then goes to what? Okay? Goes to this back sprocket, right? Why is this back sprocket important? Why is that back sprocket important? Why? So what's the same about the edge of the outer edge of the wheel as opposed to that sprocket? There's only one thing that's the same. They both spin the exact same. Okay? Their rotational speed, their angular speed, their rotational speed is the same. So they make the same amount of rotations, which is what we found. We found how much rotation that they make. Right? Okay? Now, what? Okay, because now we can jump to the outer of the wheel. But what do we want our answer in? Feet. So we're going to change this at the very, very, very end to calculate how many feet that is. What do we got? Yeah, time for report. Is it 335? Oh, no, it is 3. Mine, because mine rounded up to the other one. Yeah, nope. I'll go with you. Oops. Yeah. 2 things to hand out today. One, I'm going to hand out to everybody, and that is your the next worksheet, 4.1B worksheet. Okay, so this is one will be due next Tuesday. The second one is, if you want it, we have a white extra credit that will also be due on Tuesday. If you choose to do the extra credit, it is up there on the cart for you to go and get.